They say fusion is just bottling a star, but that is a massive understatement. To unlock unlimited energy on Earth, we can't just copy the sun, we have to completely crush its performance. And in the brutal world of science, there is a terrifying gap between a cool experiment and a machine that actually powers our world. Fusion, the ultimate broken promise. It has a notorious reputation. You've definitely heard the running joke. Fusion is always 30 years away, and it always will be. We've been fed decades of explosive headlines, gigantic experimental reactors, and mind-blowing promises, only to face the crushing reality that absolutely none of them are powering your home today. This endless cycle has left millions suspecting that fusion isn't a miraculous breakthrough, but a total scientific scam. That deep skepticism makes sense, but it's actually dead wrong. Believe it or not, physicists aren't the ones promising miracle timelines. Here is the shocking truth. A genuine, earth-shattering breakthrough happens. The media goes absolutely wild with hype, and the public is tricked into believing free energy is arriving tomorrow. But to be fair, the early days were fueled by insane, uncontrollable optimism. Why? Because nuclear fission moved at terrifying speed. The very first controlled fission reactor, Chicago Pile 1, went critical in 1942. Just a few short years later, apocalyptic fission bombs ended a world war, and the first commercial reactors exploded onto the scene by the mid-50s. Fusion felt like the unstoppable next step. By the early 50s, humanity already knew this force powered the sun itself. Mind-bending fusion reactions were actually created in labs back in the 1930s. Then, in 1952, the terrifying hydrogen bomb unleashed fusion on a catastrophic, unimaginable scale. Right then, scientists were furiously racing to build multiple fusion reactors all at once. In the United States, the top-secret Project Sherwood chased magnetic confinement methods like the legendary Z-pinch. In 1951, Lyman Spitzer at Princeton designed the mind-blowing stellarator even before the hydrogen bomb was tested. A few years later, the Soviet Union unleashed the very first Tokamaks. By the late 50s, these beasts were crushing the competition so brutally that almost every other design was thrown in the trash. And the craziest part, they were all successfully producing fusion. With that kind of explosive progress, it was totally logical to believe limitless power was just a couple of decades away. It wasn't some crazy lie, it was a thrilling prediction based on unstoppable momentum. Yet, fusion has been almost here for nearly a century. Governments have burned through tens of billions of dollars chasing this holy grail. The absolute smartest minds on Earth have sacrificed their entire lives to crack the code. But when we flip a light switch today, we are still relying on dirty coal, gas, aging fission reactors, and solar panels, not miniature stars. This isn't about selling a fusion fantasy. While the long-term future looks incredibly bright, and commercial fusion would literally change human history, it is not a magic wand. It won't instantly make power free or effortless overnight, and nobody has a crystal ball to predict exactly when this miracle will arrive. There are no empty promises here that the very next reactor will magically fix everything. Instead, get ready for the brutal, unfiltered truth. We are going to expose exactly why fusion is insanely difficult, the massive, terrifying problems these reactors are desperately trying to solve, and what scientists actually mean when they promise practical fusion power. Because the shocking secret about fusion isn't that it doesn't work. The real nightmare is that it just isn't working enough. Believe it or not, fusion reactions are happening all around us, all the time. Scientists have been sparking this terrifying power in labs for nearly a century. The shocking truth: we already know fusion is 100% real. Just look at the blazing sun or the devastating fury of a hydrogen bomb. But the ultimate billion-dollar mystery remains. Can we actually tame this beast? Can we cage a star and turn it into a cheap, unstoppable power plant instead of just a wild science experiment? To grasp why caging a star is so insanely difficult, we must uncover the mind-blowing reason humanity is utterly obsessed with it. Why do brilliant minds keep risking everything despite decades of crushing failures? Here is the jaw-dropping truth: fusion is the holy grail. It is the absolute perfect energy source we've been dreaming of. It unleashes a mind-numbing explosion of power from practically nothing. When tiny atomic cores smash together, a microscopic sliver of mass vanishes. But that missing ghost mass erupts into pure, unstoppable energy. Just a thimble of this fuel could power entire megacities forever. It is Einstein's legendary equation brought to terrifying, glorious life. But here is the real kicker. The fuel is literally everywhere. We are talking about hydrogen ripped straight from ordinary tap water. Forget fighting brutal wars over rare minerals or bowing to greedy nations hoarding fossil fuels. If we unlock this secret, the global energy crisis dies overnight. Energy scarcity will be erased from human history. And the safety profile? It's completely unbelievable. Unlike traditional nuclear plants, fusion cannot melt down. There are absolutely zero runaway chain reactions. If a single thing goes wrong, the raging plasma instantly dies, the machine cools, and the danger vanishes in a heartbeat. The physics of a catastrophic explosion simply do not exist here. Now, nothing is entirely without risk, and yes, modern nuclear plants are incredibly safe today. But fusion is a totally different beast. When a fusion reactor fails, it doesn't make the evening news with a catastrophic blast, it just quietly goes to sleep. Even better, it completely obliterates the most toxic political nightmare of our time, forever waste. Sure, fusion creates some radiation and parts get radioactive over time, but it absolutely does not spew out that terrifying, high-level toxic sludge that haunts our planet for tens of thousands of years. Forget the endless bitter debates over burying nuclear trash. Fusion completely destroys that political roadblock. It is the ultimate dream, all the godlike power of nuclear energy, with zero toxic baggage, as long as we don't let new paranoid myths ruin it first. So, if this is the ultimate god-tier solution, infinitely powerful, spotlessly clean, and insanely safe, why on earth aren't we using it right now? The brutal truth? Taming this beast requires conditions so extreme they defy human comprehension. We aren't just pushing technology to the edge. We are violently ripping past the physical limits of what any machine on Earth can actually survive. You probably think it's just about insane heat, right? The sun is a fusion monster and it's scorching. So if we just blast something until it's hotter than the core of the sun, shouldn't it just work? That assumption is a massive billion-dollar lie. Heat alone is absolutely worthless to fusion. To cage a star, you must conquer mind-bending density, crushing pressure, impossible confinement, and perfect razor-edge stability. It comes down to forcing particles to violently collide in the perfect way and trapping that explosive chaos before it falls apart. The sun gets away with being a shockingly weak fusion reactor just because it's absolutely gigantic. Its actual power output per pound is incredibly pathetic. Single protons trapped inside the solar core can wander aimlessly for millions of years before they ever trigger a single fusion event. The sun survives not by burning furiously, but by burning painfully slow, letting crushing gravity do the work of holding it together. To expose this mind-blowing inefficiency, it takes 4,000 tons of the sun just to generate 1 single kilowatt of power, barely enough to run a cheap microwave. 4,000 tons. With that terrible power ratio, a standard solar panel looks like absolute alien magic. Instead of making 1 measly kilowatt, it would be pumping out tens of thousands of kilowatts. It could even harvest massive energy from nothing but the faint glow of moonlight. It feels insane to call the sun weak, but on this specific scale, it truly is a massive underperformer. Shockingly, it's still stronger than countless other stars, some producing just a few watts for the exact same mass. An Earth-based fusion reactor does not have that luxury. If fusion is ever going to power human civilization, it must unleash infinitely more energy per pound than the sun ever could. It must unleash that energy on human timescales, inside machines that fit in buildings, under conditions controlled with razor-sharp precision. The goal isn't just to build a star. The mission is to completely outclass one. And that one terrifying requirement explains exactly why fusion remains the ultimate, unbeatable scientific nightmare. To grasp how this is even attempted, the brutal reality of fusion must be exposed. revealing exactly why copying the sun was a guaranteed path to failure. The shocking truth of what fusion is and isn't. To realize why humanity must conquer something as colossal as the stars, the hidden violent world of microscopic atoms must be ripped wide open. Nuclear power is usually thought of as fission, taking a massive, highly unstable atom like uranium and bombarding it with neutrons until it violently shatters. Inside standard reactors, these are sluggish, low-energy impacts, morphing into highly unstable temporary isotopes in a process known as neutron capture, not fusion. The neutrons must actually be slowed down so they don't just violently ricochet and escape. They need to get trapped inside the nucleus, triggering a short-lived, unstable fission explosion. The blistering heat is then harvested as those radioactive fragments and neutrons smash around inside the reactor's water like bullets. True, unbridled fusion is the exact opposite. It takes the smallest, most basic atoms in the universe, like hydrogen isotopes, and violently crushes them together at mind-bending speeds to forge something heavier, like helium. When those nuclei finally smash together, the newly forged nucleus has slightly less mass and energy than the original pieces. That leftover explosive excess is what gets harvested for limitless power. But when forcing these tiny nuclei to merge, a catastrophic roadblock appears that neutrons never have to face. Electric charge. Every single atomic nucleus holds a positive charge, and positive charges violently repel one another. This is the infamous Coulomb barrier. Imagine trying to desperately crush two incredibly powerful magnets together, North Pole to North Pole. Thanks to the brutal inverse square law, the closer they get, the more aggressively they fight back. To force these particles to fuse, you must conquer an invisible wall of repulsion, slamming them close enough for the mighty strong nuclear force to dominate. This force is a staggering 100 times more powerful than electromagnetism, but it has absolutely zero reach. Think of it like the universe's most extreme superglue. We literally call its carrier particles gluons, but they only activate when nuclei are practically touching. Push them across that brutal finish line, and they violently snap together, unleashing a mind-blowing shockwave of pure energy. Fail, and they just helplessly bounce off into the void. This shocking reality is exactly why fusion isn't a simple chain reaction like fission. You can't just spark a flame and walk away. You have to violently force every single collision, millions of times every single second, fighting a relentless force desperately trying to rip your fuel apart. Now prepare to have your mind blown. The sun is actually a terrible nuclear reactor. We are constantly told we need sun-level heat to unlock fusion on Earth. That is a massive, dangerous understatement. The sun's core burns at a blistering 15 million degrees Celsius. Sounds insane, right? But for a microscopic proton, that is literally freezing. At that pathetic temperature, most protons simply lack the speed to smash through their mutual repulsion. They just bounce off each other over and over for millions of agonizing years. The sun's gargantuan mass is only good for crushing pressure and trapping heat deep inside its core. Almost nothing escapes. The terrifying truth is, the sun only survives because it is so unfathomably massive that it can afford to be lazy. Even though the odds of two protons actually fusing are astronomically impossibly low, the sun hoards octillions of them, crushing them together. It wins through brute force volume, not raw intensity. If you somehow teleported a glowing cubic meter of the sun's core right into your backyard, it would generate a pathetic 275 watts of fusion power. That is barely enough to light up a handful of ancient dusty light bulbs. Even though the core is the most intense part of our star, its actual fusion output is shockingly weak. Sure, it would radiate a lethal, blinding wave of thermal heat as it rapidly cooled down and choked out the fusion process, but the energy generation itself, a complete joke. That laughable power-to-mass ratio would be absolutely, completely worthless for any modern power plant. And even if we look at the most colossal stars in the universe, the brutal math still fails us. Stars range from tiny red dwarfs to monstrous hypergiants, and their fusion intensity can explode by a factor of billions. Inside those cosmic monsters, crushing gravity forces fusion to happen faster, but they still take millions of years to burn through their fuel. By human engineering standards, they are painfully, agonizingly slow. Sure, using a rare fuel like deuterium makes things significantly easier. Even failed stars, known as brown dwarfs, glow fiercely in their youth because they ignite this exact deuterium fuel. They burn through it relatively fast, but in cosmic time, fast still means tens of millions of years. Here on Earth, we are fighting a desperate battle. We don't have the crushing gravity of a star on our side. We absolutely do not have millions of years to wait for power. And we definitely cannot build a reactor the size of a sun. We are literally trying to cram an apocalyptic power source inside a single building. And it has to justify its jaw-dropping billion-dollar price tag by pumping out massive amounts of energy right now. This is the terrifying heart of the Tokamak problem. To build a working reactor, we must force our fuel to fuse millions of times faster than it does inside the sun. That means a measly 15 million degrees just won't cut it. To get the insane reaction rates we desperately need, we have to push the limits to a staggering 150 million degrees. That is 10 times hotter than the boiling core of our sun, or maybe even hotter. We are engineering conditions far more violent and extreme than the heart of almost any star in the entire galaxy. We aren't just trying to bottle a star. We are trying to trap a raging supersun inside a box, fueled by deuterium. And as you can guess, building a box that can trap a supersun without instantly vaporizing is the ultimate engineering nightmare. Enter quantum tunneling. This is how we cheat the universe, winning by sheer statistics, not strength. Up to this point, this entire concept sounds completely impossible. Atomic nuclei violently repel each other, and the strong nuclear force only kicks in when they practically touch, then pure brute force should absolutely fail. Even at these mind-melting temperatures, most nuclei simply lack the raw energy needed to smash through the Coulomb barrier. They should just bounce off each other forever. And in a purely classical universe, they absolutely would. But fusion actually happens, both in blazing stars and our billion-dollar reactors, because our universe hides a mind-bending secret. It is not purely classical. Down at the microscopic quantum level, particles refuse to act like solid objects with exact, predictable positions and energies. Instead, they morph into bizarre probability distributions. Their energy, position, and momentum are real, but incredibly fuzzy, with a chaotic uncertainty permanently baked right in. And that uncertainty? It isn't just a glitch. It is the ultimate cosmic loophole. This jaw-dropping phenomenon is called quantum tunneling. Instead of imagining particles as simply having enough energy or failing completely, you have to think about the crazy odds. Imagine a nucleus needs exactly 10 units of energy to crash through the Coulomb barrier. If it only brings 9, classical physics screams that it's a hard no. But quantum mechanics breaks all the rules. That 9 comes with a tiny yet very real chance of magically acting like a 10. An 8 has a smaller chance. A 7 has an even slimmer shot. But incredibly, even a 1 has a chance. Sure, if the odds are that astronomically low, it might take literal eons to happen even once in the entire universe. That is exactly how bizarre iron stars might suddenly spark into existence trillions of years from now. Shockingly, most fusion in our modern stars happens with 8s and 7s, not 10s. This means almost every single collision is a total failure. Nuclei violently smash together, violently repel, scatter, and fly apart into the void. But every once in a while, against all odds, the cosmic uncertainties line up perfectly. A particle that has absolutely no business making it suddenly does. When that miracle happens, the nuclei get just close enough for the strong nuclear force to instantly take over, violently snapping them together and unleashing massive energy. They don't just smash through the barrier, they literally ghost right through it. This bizarre trick is not common. It is definitely not efficient. But the chance is not zero, and that is all the spark fusion needs. Temperature still matters enormously because hotter conditions mean faster particles and a chaotic frenzy of collisions. But raw heat alone is never enough. Fusion is a brutal game of cosmic statistics. You need an unfathomable number of particles violently colliding over and over again just so those rare, miraculous events can actually add up to something useful. In reality, far more of these collisions fail than anyone ever realizes. This is the shocking reason we desperately prefer deuterium over regular hydrogen as our ultimate fusion fuel. It has a significantly lower Coulomb barrier. The other massive secret? When protons ram into each other as basic hydrogen, they almost never stick together, completely wasting the entire explosive event. When two protons violently smash together, they usually form a doomed split-second pair before violently ripping apart. But in that microscopic flash, there is a shocking chance for something truly explosive to happen. Deep inside that chaotic six-quark collision, a bizarre mutation transforms one proton straight into a neutron. The mind-blowing result? Deuterium. A proton and neutron lock together while a positron, the terrifying antimatter twin of the electron, is violently blasted away. Imagine two runners sprinting past each other and high-fiving. Almost every single time, absolutely nothing happens. They touch for a fraction of a second, but there is a freak 1 in a billion chance that lightning strikes at that exact millisecond, permanently fusing them into a brand new entity. This insane cosmic lottery is exactly how stars ignite. Billions of collisions fail. But those incredibly rare perfect strikes, they are the secret engine keeping the entire universe glowing. But here on Earth, we absolutely cannot wait around for cosmic lightning to strike. That is why we hijack the system, using superfuels like deuterium and tritium, heavy hydrogen isotopes packed with pre-installed neutrons. This hacks the odds, but even with this overpowered fuel, we are still gambling with the brutal laws of the cosmos. Quantum tunneling makes this miracle possible, but it definitely does not make it easy. And that unleashes our next massive nightmare, a terrifying engineering crisis that makes nuclear physics look like child's play. We have to trap a star, the ultimate plasma problem. If fusion was only about surviving hellish temperatures, we could just brute force our way to victory. Just blast it with heat, trap it, and wait. But fusion fuel isn't a solid, it's not a liquid, and it's definitely not a normal gas. At these apocalyptic temperatures, atoms are violently shredded into plasma, a raging, boiling storm of naked nuclei and rogue electrons, screaming around at mind-bending speeds. Plasma is an absolute monster. It conducts raw electricity, spawns its own chaotic magnetic fields, and reacts with explosive violence to the tiniest glitch. But the most terrifying part, plasma cannot touch anything solid. I mean, it can, but so can a lightsaber. The solid object simply ceases to exist. And this isn't your everyday plasma either. We are dealing with a beast 1,000 times faster and 1,000,000 times more destructive than a lightning bolt. If this raging storm touches the reactor wall, the wall instantly vaporizes, the plasma dies, and the reaction completely collapses. Game over. So the ultimate billion-dollar challenge of fusion isn't just sparking the fire, it's holding a burning star without ever touching it. The only weapon we have to fight this monster is extreme magnetism. Because this plasma is loaded with charged particles, it is completely chained to magnetic fields. These charged particles are forced to spiral along invisible magnetic force fields. You can never trap plasma in a physical box, but you can force it into a high-tech magnetic cage. But in reality, this superheated beast does absolutely everything it can to break free. The magnetic fields must be flawlessly shaped and constantly warped to stop the plasma from writhing, thrashing, and tearing itself apart. Microscopic flaws explode into chaos. Tiny ripples mutate into violent reactor-killing shockwaves. Heat bleeds out, and the hotter this monster gets, the harder it is to cage. Magnetism is also a nightmare to control, because unlike electricity, these massive magnetic fields are almost impossible to block. And to make this nightmare worse, our absolute best shot at creating these massive magnetic fields relies on superconductors. But they do not survive at normal temperatures either. They demand mind-numbing, freezing conditions. This is exactly why fusion reactors are never passive machines. They are hyperactive beasts, desperately fighting to control chaotic plasma that violently wants to tear itself apart. This is where the crazy geometry kicks in. Try trapping boiling plasma inside a straight magnetic tube, and it instantly blasts right out the ends. To trap it long enough to actually matter, the magnetic field must ruthlessly loop back onto itself. The ultimate hack? Bend the entire chamber into a massive ring, a giant donut, and wrap intense magnetic fields completely around it. This wild concept leads straight to the legendary Tokamak. Tokamaks are not built because they are easy. They exist because they brutally crush multiple impossible problems at once, sealing the magnetic bottle, taming the plasma, and forcing fuel to circulate just long enough to ignite. This gives us the iconic name Tokamak, which is actually just a clever Russian abbreviation for a toroidal chamber packed with massive magnets. Other mind-blowing designs, like the Stellarator and the Z-Pinch, are just as insanely literal. Stellarator translates to Star Maker, while the Z-Pinch violently crushes plasma using its own magnetic field. The Z-Pinch is shockingly simple. It mercilessly crushes the plasma into a straight line. But here is the catch. When you squeeze plasma that hard, it violently squirms right out of your grip like a slippery wet bar of soap. It is so incredibly unstable that it usually rips itself apart before any real fusion even sparks. But massive breakthroughs are happening, and one day this tech might actually conquer the grid. Every single design faces terrifying hurdles, and fixing one problem usually spawns a new nightmare. Stronger magnetic fields create massive structural stress. Tighter confinement triggers terrifyingly violent explosions when things go wrong. Building bigger machines helps, but they become astronomically expensive and totally unforgiving. It is exactly why we do not just detonate hydrogen bombs inside giant underground lakes to boil water for a turbine. If your fusion reactor has to be larger than an entire city just to generate power, you are in deep trouble. After all, we could always just beam down microwave energy from space solar panels, harvesting power directly from the giant fusion reactor we already orbit, the Sun. The shocking truth? It is not about whether we can make fusion work we already have. The real impossible challenge is making it cheap. In a city-sized mega reactor? That is definitely a financial disaster. This is the terrifying heart of the Tokamak problem. Fusion is not just about sparking extreme conditions, it is about trapping them, dominating them, and doing it flawlessly, over and over again. It must run like an unbreakable power grid, not a fragile science experiment. Once you grasp this insane reality, we can finally reveal why tokamaks are actually dominating the race and where they fail miserably. Here is what tokamaks actually solved. It is dangerously easy to look at the endless timeline of fusion and claim that nothing has changed. But that massive illusion comes from only staring at the finish line, totally ignoring the mind-blowing distance we have already conquered. Early tokamaks completely failed to trap plasma at all. Back in the 60s and 70s, keeping this starfire stable for even a tiny fraction of a second was hailed as a massive miracle. Violent instabilities instantly shredded the plasma the exact second it formed. Blistering heat bled away faster than it could ever be pumped in. Reaching fusion temperatures was just a desperate fantasy, not a reality. But over time, that impossible reality shifted, painfully slowly and at an astronomical cost. The shaping of these godlike magnetic fields finally leveled up. Plasma shapes mutated from basic circles into bizarre, meticulously sculpted forms, instantly crushing chaotic turbulence. Heating methods absolutely exploded. We went from basic ohmic heating to unleashing monstrous neutral beam injectors and insane radio frequencies, blasting specific zones of the plasma with unimaginable power. Hypersmart control systems evolved at lightning speed, obliterating dangerous instabilities before they could even trigger a catastrophic cascade. The ultimate result: a total game changer. Confinement skyrocketed by mind-blowing orders of magnitude. Temperatures didn't just climb, they violently erupted. From a measly few million degrees to tens of millions, eventually smashing right through the impossible 100 million degree barrier. Plasma lifespans stretched from pathetic milliseconds to seconds, and shockingly, all the way to minutes. Scientists track this using the legendary triple product, a single ultimate metric combining extreme heat, crushing density, and maximum containment time. Plot that number over 50 years, and the curve is absolutely jaw-dropping. For decades, it literally obliterated Moore's law. Let's be brutally honest, we are thousands of times better at fusion today. Rolling your eyes and claiming fusion is a dead end when we are literally orders of magnitude beyond the terrifying era of hydrogen bombs. That isn't rational skepticism. It's pure ignorance of the colossal, literal, star-sized problem we are trying to conquer. We haven't been standing still. We've been scaling a terrifying mountain that turned out to be vastly more massive than anyone ever feared. By the 1990s, Tokamak smashed through a massive psychological wall. Epic facilities like JET in the United Kingdom triggered actual deuterium-tritium fusion, unleashing raw megawatts of power. Recently, JET sustained a blistering fusion burn, violently unleashing 59 megajoules of energy in just 5 seconds. Sure, that won't power a megacity, it's roughly equal to a gallon of gas. But it proved something infinitely more profound. Fusion plasma could actually be insanely hot, incredibly dense, and perfectly stable all at once. And that was never guaranteed. Tokamaks didn't entirely solve fusion, but they cracked enough mind-bending physics to expose the true, terrifying bottlenecks. Once confinement was conquered, a far more brutal nightmare took its place. The ultimate tokamak problem. So what exactly is this massive roadblock today? It's not that fusion reactions are impossible. They happen. It's not that plasma can't be trapped. It can. Modern tokamaks routinely blast past fusion temperatures, holding the plasma long enough to trigger sustained, violent reactions. The horrifying truth? None of this magically creates a working power plant. A tokamak can generate incredible fusion energy, yet still devour way more power than it actually spits out as electricity. Superheating the plasma, firing up colossal superconducting magnets, running extreme cooling systems, and powering hypercomplex hardware drains massive amounts of energy. Fusion neutrons carry a staggering 80% of the reaction's energy. But capturing that raw power without completely obliterating the reactor itself, that is a monumental nightmare. Here is the darkest irony of all. Those high-speed neutrons are the ultimate prize, but they are also a deadly poison. They carry the exact limitless energy we desperately want to harvest, but as they violently explode out of the plasma, they smash into the reactor walls like a relentless subatomic sledgehammer. They don't just make the materials dangerously radioactive through a process called activation. They literally rip apart and physically mutate the very atoms of the machine itself. They blast tiny gas bubbles and violently rip atoms right out of their crystal lattice, mutating ultra-tough, insanely expensive alloys into something as fragile as shattered glass. The terrifying truth? As our fusion tech gets better, the hellscape inside the reactor becomes exponentially more brutal. This triggers a devastating cycle of endless downtime, costly repairs, and massive replacements that absolutely crushes our current designs. A real power plant can't just survive on a heroic split-second burst of glory. It must relentlessly dominate day and night for decades. Right now, our most mind-blowing experiments are just pathetic blips compared to the monstrous, relentless demands of a modern city's power grid. So the ultimate tokamak crisis isn't about whether fusion actually works. It's about mutating a machine that spits out lucky, flashy sparks into an unstoppable beast that pumps out cheap, reliable electricity to power the world. It's a high-stakes war of brutal economics, mind-bending physics, and impossible engineering. Fusion has finally crossed the impossible line, but these nightmare challenges won't just vanish into thin air. They demand brutal honesty about what true victory looks like and which billion-dollar gambles are actually working versus which ones are just getting absurdly massive. And this inevitably drags us to the most legendary, controversial mega project of them all, and the shocking limits of simply building bigger. We have to talk about ITER. ITER is hyped up as the ultimate fusion savior, the god machine that will finally prove unlimited energy is real. But that massive hype, it's dangerously misleading. Prepare to be shocked. ITER is not designed to power your city. It won't pump a single watt of electricity into the grid, and it will never run a commercial power plant. Its real mission is far more secretive and infinitely more critical. ITER exists to answer one terrifying question. What actually happens when you supersize a tokamak to the scale of a monstrous power plant? Until now, fusion research has been trapped in a frustrating limbo. Tiny machines are cheap, easy to build, and simple to sell to cautious investors. But they bleed out scorching heat and particles way too fast to ever survive as real working reactors. Giant machines can trap that boiling plasma better, but they unleash a nightmare of new threats. Catastrophic mechanical stress, devastating material damage, and mind-boggling astronomical costs. ITER is the ultimate high-stakes gamble meant to smash right through that barrier. Its singular epic goal is to achieve a fusion gain factor known as Q of a massive 10. That means detonating 10 times more raw fusion power inside the boiling plasma than the colossal energy it takes to ignite it. Not 10 times more electricity, not grid power, just undeniable, explosive proof that at a gigantic scale, the laws of physics actually obey our wild predictions. I think that sounds disappointing. Think again. Smashing this threshold changes everything, because trapping that starfire gets drastically better as it grows. Massive plasmas hold their blistering heat far longer. Violent turbulence shifts entirely, and chaotic, deadly instabilities suddenly become incredibly easy to tame. For decades, scientists have desperately prayed this theory was true, but ITER is the very first titan massive enough to actually prove it. But beware, because ITER will also expose the dark, terrifying half of this energy revolution. A reactor pumping out godlike fusion power is completely worthless if the entire machine around it violently crumbles to dust. High-speed radioactive neutrons will brutally bombard the reactor walls, shredding materials, destroying delicate superconducting magnets, and turning safe components dangerously radioactive. Unimaginable heat must be siphoned off flawlessly without melting the very structures built to contain it. Fixing these massive machines must be possible without shutting down the entire grid for years at a time. ITER won't magically fix everything, but it will expose exactly how terrifying these roadblocks truly are. And that is the shocking truth. Simply building bigger reactors doesn't instantly create a working power plant, but it does destroy the illusions. It reveals if we are facing minor engineering bumps or absolute world-shattering dead ends. Fusion always feels incredibly close, yet agonizingly out of reach. But understanding these brutal engineering realities is absolutely crucial for our future. Because limitless energy isn't just a luxury, it is pure survival. A mind-blowing, high-output source like fusion could literally mean the difference between total societal collapse and human survival during a catastrophic new ice age. When the environment turns deadly, adapting our technology is the only way out. So with survival on the line, we must ask, are there other shocking ways to unlock this ultimate power? Are tokamaks the only secret weapon we have? Absolutely not. Enter the Stellarator, a mind-bending machine that trades simple operation for insane, twisted geometry. In theory, they can trap boiling plasma forever, completely ditching the pulsed currents that tokamaks desperately need, but they require unimaginably complex magnetic force fields. Modern Stellarators are blowing their predecessors out of the water, and they might just be the ultimate key to non-stop, limitless power. Then there is inertial confinement, blasting microscopic fuel pellets with devastating laser beams. This method has seen explosive, jaw-dropping progress recently. But it faces terrifying scaling nightmares, especially when trying to fire fast enough, boost efficiency, and turn violent, split-second bursts into a smooth, endless river of electricity. And do not forget the wild, booming world of private fusion startups. They are experimenting with everything from miniature tokamaks to magnetized target fusion, and even bizarre designs that barely look like reactors at all. Some of these radical ideas will change the world. Others will crash and burn. A few might even be outrageous scams run by absolute frauds. But aside from the fakes, almost all of these brilliant projects are desperately, shockingly underfunded. We desperately need to investigate these underdog technologies, but here is the brutal reality. Not a single one can escape the unforgiving laws of physics. Every single machine must generate massive energy faster than it drains it. They must somehow survive being blasted by their own deadly neutron radiation. And they must run flawlessly, be incredibly easy to fix, and produce dirt-cheap electricity to crush the competition. There are countless paths to victory, but absolutely zero shortcuts. So, where does this leave the ultimate dream of fusion? Today, it sits in a bizarre high-stakes limbo. It is no longer just wild science fiction. It is no longer just math on a chalkboard, and the core physics are finally solved. But it is still not powering our cities. Fusion has officially crossed the terrifying line from totally impossible to insanely difficult. And these monumental challenges will never be solved by cheap hype or fake deadlines. These forces demand brutal honesty about the shocking costs. Nature is stubborn, but human ambition is unstoppable. The universe doesn't care about our desperate dreams. It demands flawless results at massive scale, surviving brutal real-world conditions for years on end. If this legendary fusion dream actually becomes reality, it won't explode overnight as a sudden magical revolution. It will creep in quietly, built on decades of failed billion-dollar machines, until one miraculous device finally sparks to life. Then, a new army of engineers will turn this sci-fi miracle into a totally ordinary, everyday reality. But even if this ultimate energy dream fails, the payoff is already mind-blowing. The desperate race for fusion has already triggered massive breakthroughs in superconductors, extreme plasma physics, and next-level materials that are secretly powering countless futuristic technologies right now. So stop thinking about fusion as just a broken promise or a tragic failure waiting to happen. It is the ultimate high-stakes test of human engineering, pushed to the absolute limit against the most terrifying forces in the known universe. We aren't just bottling a star. We are trying to build a machine that does something infinitely harder and gambling everything to see if the shocking price tag is actually worth it. With massive technological payoffs happening right now, and the ultimate prize being literally infinite clean energy, the final answer is as blindingly obvious as the blazing sun itself.